This video will show you how to handle a mass when it's on an inclined plane. So I like to slant my inclines lower at the right, doesn't matter, but makes it just a little bit easier. The angle of the incline is always this angle here between the horizontal and the incline. This is a 90-degree triangle. So when we put a mass on this incline, what we do is we let our axes, our X and Y axes, actually be parallel and perpendicular to the incline. So this is how we do our X and Y axes, because the mass obviously moves staying in contact with the incline, which means it's moving in the X direction, which makes it that much easier to analyze. Now, the force of gravity on this mass will always point straight down. So that's the force of gravity. And what we have to do here is, because we need the components of this force of gravity that are in the X and Y directions, we have to make a box around this gravity vector. Make a box like that. And remember, the X and Y components are the parts of the force that lie in the X direction. So that'd be FGX, and FGY would be into the incline like that. Now, FGX is the part of gravity that makes the block slide down the plane, and FGY is the part of gravity that keeps it stuck to the surface. Now the question is, how do we get these two components? Well, it turns out that this angle is the same as theta. And you can either just memorize that, or you can, let's just look over here at a really shallow incline. And we put the box on there, and we have this XY axis, and FGY is here, and FG is here, straight down. And see how there's a really small angle here, theta? That's because this is a small angle here, theta. Okay, so it is the angle between FG and FGY that is theta. Okay, so remember I said that we're going to be having triangles that don't necessarily always have the X component as the cosine. So let's draw that triangle again. We've got this funny looking triangle now where the hypotenuse is always the magnitude of the vector, that's FG. And then the two sides here are FGY and FGX, where up here is the angle, and this is 90 degrees. So now let's do our sine, cosine, tangent. So the sine of that angle is the opposite side, FGX, over the hypotenuse, FG. And the cosine of that angle is FGY, the adjacent side, over FG. So this is how you get that FGX goes with the sine of the angle, and FGY goes with the cosine. Now, you absolutely have to memorize that or figure it out every single time. And so what I recommend you do every time you get a problem where you've got a box on an incline, or a skier on an incline, or any kind of object on an incline, is you simply draw the box. Now, you don't need FG, because once you have its components, you've got the effect of gravity. So I would just immediately put on FGX, which is FG sine theta. And I remember this is the slippery component of gravity. Slippery and sine go together, the S, slippery. Or sometimes you can call this the down slope component of gravity. Down slope, slippy slope, gravity. Now, it doesn't matter whether this box is sitting still, going up, going down. If it's sitting on that incline, gravity is pulling it with a force equal to FG sine theta. And then the other component, keeping it on the surface so it doesn't fly off into outer space, FGY, is FG cosine theta. And the way I remember that is close. So this is what keeps the box close to the surface. And this is, I call this the in slope. It's the one pulling the box into the slope, component of gravity. And you absolutely have to memorize that, because every single problem you do on an incline, you will need those two components. Now, like I said, that doesn't matter whether this box is going up, down, or just sitting there. There will also always be a normal force, which is the force of the surface on this box. And remember, the normal force is the force due to surface. And that's what keeps the box from falling through the surface. Now, it's not going anywhere. It's not going into the surface or out of the surface. So this is exactly balanced by FGY. So this is equal to FG cos theta. And so it will always be true for you in this course that the normal force is Fg cos theta for a box on an incline. Okay, so this is the case. It is not just equal to Fg, like it is on a flat horizontal surface. It's equal to Fg cos theta. Okay, now friction. When we bring friction in, remember this is always parallel to the surface. And what type of friction it is depends on the problem. And the direction of friction depends on which way the box is going. So let's look at three possibilities. Case one, box is stationary. Okay. If the box is stationary, which can often happen, you stick a box on an incline, just sits there. It means that, remember, you always have Fg sine theta down the incline. If it's stationary, the thing holding it there, counteracting gravity, would be friction, static friction. That would be this way, F friction, and this would be static. Now, how would we figure out what that is? If it's just sitting there, these two forces balance. So the force of static friction must exactly equal the force of gravity sine theta. Okay, that's if it's stationary. Now, remember also that friction forces, static friction, are calculated using the coefficient of static friction times the normal force. And because it's on an incline, the normal force, which we just wrote a minute ago, is Fg cosine theta. And so that is how you get the force of friction. It's mu s Fg cosine theta. Okay, so if you wanted to draw those two, well, we've already done that. We know what Fn is. Fn is this Fg cos theta. Okay, so that's if it's stationary. Case two, it's sliding down. Okay, so now if it's sliding, then gravity is always the same, Fg sine theta down the incline. But now it'd be kinetic friction, and it would point against the motion, opposite the motion. So this would be the force of friction kinetic. So this is Ff kinetic. And that would still be mu k Fn, and Fn would still be Fg cosine theta. So the only difference here between case one and case two is if it's sliding, you use the kinetic coefficient of friction, mu k. Now, whether that Ffk equals Fg sine theta, which is possible, it just means this would be going at a constant speed, or whether it's less, in which case it's simply slowing this box down a little bit. But it will never be more than Fg sine theta. It will never suck the box up the incline. So it's either equal to or less than Fg sine theta. Okay, so that's case two. Now case three, you may be pushing it up the incline. So this would be moving up incline. Now it could be because you're pushing it up, or it could be because you sort of give it a little toss and it's just sliding up and then eventually it'll stop and come to rest. But if it is moving up, so this is now moving up, gravity is still down. Gravity never changes. Gravity is always Fg sine theta down the slope. But now if it's moving up, the force of friction, which will be kinetic again because it'll be sliding, will be opposite the direction, will be this way. Force of friction kinetic. Okay, so that will be opposing the motion as it goes up. And so the force, but it's the same formula. Force of friction kinetic is still mu k Fn, and it's still mu k Fg cos theta. Okay, so that's just about every possibility for a mass on an incline. Maybe I'll just do a quick example where we have some numbers. So I'll get my calculator here. So let's do an example. Let's calculate force of friction for a 10 kilogram box sliding down now you'd be surprised, a 45, you cannot stand up on a 45-degree incline. So a 20-degree incline is still a pretty steep incline. A 20-degree incline, if the coefficient of friction is, let's say, 0.2. So whatever the surfaces are, it's 0.2. Okay, so let's do this. So we'll draw our box. This will be 20 degrees. Down slope will be Fg sine theta. The force of gravity is mg sine theta. So this would be 10 kilograms times 9.8 newtons per kilogram times the sine of 20, sine 20 degrees. Okay, so that downslope force, quickly put that on my calculator, would come out to be 33.5 newtons. Okay, so that's the Fg sine theta. Okay, now the normal force, Fn, is Fg cos theta. And so this would be mg cos theta. So that would equal 10 kilograms times 9.8 newtons per kilogram. And I get that to be 92 newtons. 92.1 newtons. Okay, so the force of friction, now this would be kinetic friction, and if it's sliding down, this force of friction would be up. And this would be kinetic because it's sliding. And so this would be mu Fn. So it'd be 0.2 times 92.1, which equals 18.4 newtons. And that is how you would get the force of friction on an incline.